Hi everyone. So last time we introduced Bayesian methods, talked about a coin flip example, and even introduced the Dirichlet distribution while sort of alluding to the notion that selecting priors that when multiplied by the likelihood give rise to posteriors of the same shape is of computational convenience. So we will turn to that concept shortly. That's the concept of conjugate priors. But before that, I'd kind of like to do a nice little sort of recap of Bayesian methods, or at least the key quantities in Bayesian methods. So we've talked about sort of the prior, and the prior is a probability distribution on the parameter theta. It is a function which is normalized, or a probability distribution which is normalized with respect to theta. We've been talking about the likelihood now for quite a while, and that's the probability of the data given the parameter theta. And this, we said, is normalized with respect to the individual data points themselves. In order to verify normalization, again, just like we had sort of explored with the coin flip, we would have to integrate over all numerical values for each one of the w's. We have the posterior, which is the probability of theta given w1 to n, and that's more or less obtained by up to a normalization by multiplying the prior by the likelihood, sort of by the rules of multiplications of probabilities. Another important thing we discussed was the predictive distribution, allowing us to anticipate a probability over the realization of the subsequent data point given the history previously observed. And again, this doesn't necessarily need to be a predictive distribution over one variable. It could be over very many. So all the way up to, for example, n prime if I choose to. And finally, the normalization that we haven't paid much attention to, and we will probably not be paying too much attention to, the evidence, which typically appears in the denominator in the expression for the posterior when we multiply the prior by the likelihood, as we had seen earlier. So to recap, what is the, how do Bayesian methods sort of proceed? So kind of the how does the Bayesian paradigm work? So the idea is first, write down your likelihood. The likelihood itself is sort of dictated by the laws of nature that determine the process that you're interested in. So, at some level, you'll have to determine what level of simplification you want in order to be able to write down a likelihood that makes the problem tractable, for instance. Once you have written down a likelihood, then write down the prior based on domain spanned by the parameters you wish to infer, right? So if you're learning a diffusion coefficient, you know that you need a prior that has support from, for example, 0 all the way up to infinity. If you're learning a discrete variable, your prior may only be sort of on positive integers, for instance. So you have to decide what the domain of the parameter is that you care about, and then select a prior. And then finally, use Bayes' rule to write down the posterior as a product of the prior and the likelihood. And just to be clear, the reason we say proportional here is because we don't care about any terms that don't explicitly depend on the parameter. So, in other words, we're ignoring all terms that, for example, only have dependency on the data, such as the evidence. If I were to remove this expression here and simply write it out as equal, then I would need to consider a term which does not depend on the parameter and is only the evidence itself. So let's go ahead and talk about priors and different kinds of priors. So, broadly speaking, there are two kinds of priors. There are uninformative and informative priors. An uninformative prior is a prior which is as flat as possible over the domain, over the range of parameter that you care to estimate. So this would be, for example, some type of, let's call it theta, let's not call it x. This would be some prior which is very flat over a large region. The one thing we have to be careful about when we work with priors is that they still need to be normalized with respect to the parameter. So if I'm literally flat over an infinite range, for example, suppose my parameter goes from 0 to infinity, then this function here is not normalizable. So we need to be a little bit careful that the prior, therefore, have some kind of termination point, and that the area of the curve, in order for the area of the curve to be equal to 1. So maybe it's the prior itself is a constant, and it's equal to 1 over theta max, such as when I integrate this, I get 1. Now, sometimes we may be able to write this as the prior is proportional to some kind of constant. So if I say, for instance, just like in the previous coin flip example that we had looked at, if I write down my likelihood as P of W1 to n conditioned on theta, that's the probability of heads, for instance, and I write this down as probability of heads minus pi n, the total number of coin flips, minus the probability minus the number of heads. And if my prior is a constant, then I find my posterior to have exactly the same form as my likelihood. And why is that? Again, here we lump in all of the constants that do not depend, not depend on theta. So that's one way to do it. But there's a couple of disadvantages with uninformative priors. First off, there's the fact that you have to put some kind of upper bound. And in practice, if you're working with a complicated problem where you don't actually know where the majority of the posterior will be concentrated, it's difficult to determine where exactly you should set an upper bound. And if their parameter goes from negative infinity to infinity, it may also be difficult to determine a lower bound. Problem number one. Problem number two. Suppose that I have a function, and let's call this intentionally P of x, which is flat in x over some region. Well, then this suggests that P of e to the x, if I carry out a variable transformation to a different variable, for example, the exponential of that variable, could be any other transformation, will not be flat. All right, so we can look at sort of how probability distributions are transformed from P of x to some other variable. And it's interesting, so this kind of seems to suggest that in x, my distribution is flat, but if I carry out a variable transformation to e to the x, or x squared, or some other transformation of x, then I find that that distribution is not flat. So it seems to suggest that there are some regions that I know more of when I transform the variable to something other than x, which I assume to be flat. So, it raises some sort of concern that, flat may not actually be as flat or as uninformative as we think. That's more of a philosophical concern, and people did start thinking about sort of probability distributions that are invariant with respect to coordinate transformations, and this led to sort of a whole area of work and things like Jeffreys priors and so forth, which we won't delve into here. But in reality, what do we really want? We don't really care if our prior has some kind of. Now we're going to plot this as p of theta versus theta. We don't really care if our prior is not completely flat, if it has a little hump, provided we aren't starting off with a prior which is extremely informative, requiring, for example, a ton of data before being able to transform this prior into perhaps the reasonable looking posterior, which for the problem may have been this bimodal distribution which I wrote down here. So a primary concern in developing priors is primarily a practical concern. And the practical concern is one of computational efficiency. And uniform priors, flat priors, have all kinds of issues related to them, in addition to the ones that I've just mentioned here, for example, having to set a lower and an upper bound, that don't necessarily make them convenient. So this kind of immediately leads us to the discussion on informative priors. So informative priors will have some shape, and ideally, or they will not, be a constant. So there's an immediate type of, if we're willing to allow the priors to adopt some kind of shape, then there's immediately a family of distributions that's worth investigating by the time you specified a likelihood. So let's talk about something called conjugate prior likelihood pairs. If I have a p of theta and I multiply it by a likelihood, it is convenient to recover a posterior which has the same form as the original prior. In other words, if you're writing a piece of code and you are collecting various data points, as you start collecting these data points and integrating them sort of into your posterior, it would be convenient not to have the posterior adopt a different mathematical form every time you throw in a new data point. So if, and it's not always the case, but if we can find a prior which when multiplied by this likelihood provides a posterior of the same form as the prior, then we call these a conjugate likelihood prior pair. Now, sometimes people use sort of abbreviated language, and they will introduce the concept of a conjugate prior. So when people talk about conjugate prior, or a conjugate prior likelihood pair, it means the same thing, except people are kind of using shorthand notation. When you say, I'm going to find a conjugate prior, what you're communicating to the other person is basically the following. I have a likelihood, and for that particular likelihood, I'm going to find a prior, which I'm calling the conjugate prior, which when multiplied by my likelihood will provide me a posterior of exactly the same form. So that kind of summarizes very briefly the notion of conjugacy, which we'll delve into next time. Thank you.